In the given figure, vector OA is 4a plus 5b, vector OB is 8a minus b, and vector OD is 15a plus 10b. Vector AB is equivalent to vector OB minus vector OA. Substituting their respective values and solving the expression, vector AB is 4a minus 6b. It is given that the lengths of A and B are 1, and to find the length of AB, we consider A and B to be orthogonal to each other. Using the distance formula, AB equals square root of 4 squared plus 6 squared, which gives 2 root 13. We will use the shoelace method to find the area of triangle AOB. If O is 0, 0, the relative positions of A are 4, 5 and B are 8, -1. We cross-multiply the coordinates of O, A, and B to get S1 and S2. The area is calculated as half of the difference between S1 and S2. The difference is 40 minus -4, and thus the area of the triangle is 22. If OCD and OAB are collinear, we need to find vector OC. Vector OC is equivalent to vector OA plus mu vector AB, where mu is a scalar value. Vector OA is 4a plus 5b, and vector AB is 4a minus 6b. Solving for this, vector OC equals 4 plus 4 mu times a plus 5 minus 6 mu times b. Alternatively, since OCD is collinear, vector OC is equivalent to lambda OD, where lambda is another scalar value. Substituting the values, vector OC is 15 lambda times a plus 10 lambda times b. From these two equations, we get 4 plus 4 mu equals 15 lambda, and 5 minus 6 mu equals 10 lambda. Dividing the first equation by the second equation gives 8 plus 8 mu equals 15 minus 18 mu. Solving for mu, we get mu equals 7 over 26. To express vector OC in terms of A and B, we calculate 4 plus 4 mu equals 66 over 13, and 5 minus 6 mu equals 44 over 13. Thus, vector OC is 66 over 13a plus 44 over 13b, expressed in the simplest form in terms of A and B.